Have you ever looked at a gadget and wondered, how does a line of code actually do something in the real world? How does software make a thing light up, or move, or react? Well, today, we're going to pull back that curtain. We're going to build an interactive device right from square one, starting with just a single spark. So let's get into it and see how it's done.
Okay, this is where we're headed today. A simple knob controlling the precise position of a motor, just like that, in real time. Now, I know it might look a little complicated, but what if I told you that you can build this whole thing by just mastering a few key ideas? Seriously, it all starts with the absolute simplest first step you can possibly imagine.
So our very first step is just learning how to create an output. And in the world of hardware, the equivalent of printing "Hello World" to a screen is making a light blink. That's it. This one simple action is the foundation for absolutely everything else that's going to follow. And here it is, this little blinking LED. It's our first real conversation with the hardware. It's the most basic test you can run, and it tells us that our tiny computer, the ESP32 microcontroller, is alive, it has power, and it's actually listening to our code. It's that fundamental check that says, okay, we're in business.
Now, the most obvious way to code this uses a command called time.sleep. It's super simple. You tell the processor, hey, turn the light on, go to sleep for half a second, wake up, turn it off, then go back to sleep. Easy, right? But, and this is a big but, this simplicity has a hidden flaw. While that chip is sleeping, it is completely and totally frozen. It can't read a sensor, it can't check if you pressed a button, it can't do anything else at all.
And that brings us to a really crucial idea. We need a smarter way. So on the left, you've got that blocking method with sleep, which is simple but honestly pretty inefficient. But on the right, that's the pro approach, a non-blocking method that uses a built-in hardware timer. Think of it like setting an alarm clock. You just tell the timer, hey, every 500 milliseconds, I want you to flip the state of this light. And then your main program is totally free to do other important stuff. This is what allows for real multitasking. All right, so we can control one light. That's cool. But what happens when we start adding more lights? Well, we can actually start to represent more complex information. We're about to turn these simple little lights into a language, the language of numbers. With just 3 LEDs, we suddenly unlock the ability to count. See, by treating each light as a bit in a binary number, where off is a 0 and on is a 1, we can represent every number from 0 all the way up to 7. This is the fundamental language that every single computer speaks. And this right here, this is the real power of binary. When we add just 2 more lights for a total of 5, we don't just add 2 more numbers to our range. No way. We expand it exponentially. With 5 bits, we can now count from 0 all the way to 31. Every single light we add literally doubles our counting ability. It's pretty amazing. This little table here kind of decodes that language for us. So take a look at the number 3. In binary, that's 0, 1, 1. So the first light is off, but the next 2 are on. Simple. For the number 4, it's 1, 0, 0. So only that first light is on. It's this simple visual pattern that forms the basis of, well, all digital information. Okay, so we've gotten pretty good at sending information out into the world with our lights, but for a device to be truly interactive, it also needs to take information in. It's time to learn how to make our system listen.
So let's think about this. How does a tiny little chip, which really only understands high and low voltages, know for sure that you've pressed a physical button? It's not quite as simple as just, getting a signal. We have to be really precise about how we set this up.
It turns out there are 2 standard ways to wire a button, and it's all about setting a default state. With a pull-up resistor, the input pin is normally held at a high voltage. It's just sitting there awaiting. When you press the button, you complete a circuit to ground, which pulls that voltage low. So for the chip, a press means the signal is going low. A pull down is just the opposite. Its default state is low, and pressing the button connects it to power, sending the signal high. And in this circuit, you can see both of those methods working right next to each other. One button is wired as pull up, the other as pull down. When you press them, they each trigger a totally different response, even though the physical action of pressing is exactly the same. Understanding this difference is just so key to building reliable inputs for any project you make. So far, we've pretty much been dealing in absolutes, on or off, high or low. But the real world is, well, it's full of in-betweens, right? What about things like a motor that needs to move to a very specific angle, or a light that needs to dim smoothly? We need a way to fake that kind of analog control using our purely digital tools. The answer is this really clever trick called pulse width modulation, or PWM for short. Just imagine flicking a light switch on and off thousands of times a second. If you leave it on for longer than you leave it off, the light is going to look brighter, right? And if you leave it off longer than it's on, it'll seem dimmer. PWM is basically the digital version of that, and it gives us super fine-grained control over things like motor speed and position. And this is what that rapid on-off signal actually looks like to a machine. This square wave shows the voltage just switching between high and low over and over again. The really important part here is what's called the duty cycle, and that's just a fancy term for the percentage of time the signal is in the on state. So a 50% duty cycle, like we see here, just means it's on for half the time and off for the other half. Now here's where the magic happens. For a servo motor, that duty cycle isn't about speed or brightness. It translates directly into a physical angle. A really short on pulse might tell it to move to 0 degrees. A slightly longer one sends it to 90 degrees, and a longer one still sends it to 180. So by precisely controlling the width of that pulse, we can control the exact physical position of the motor. It's so cool. And that brings us to the grand finale. We have learned all the individual pieces: output, input, and that analog-like control. So it is time to combine all of these building blocks into that complete, interactive system we saw at the very beginning. Let's do it. The last piece of our puzzle is an analog input. See, unlike a button that's just on or off, a potentiometer, which is really just a fancy knob, can give us a whole range of values. As you turn it, it changes its resistance, which gives our chip a changing voltage that it can read as a number. It's basically a volume knob, but for data. The real key is how we connect that input to the output. Our knob gives us a value somewhere between 0 and about 4095, but our motor, it needs a PWM value somewhere between roughly 25 and 125. This single line of code is the magic translator. The map function just takes that big input number from the knob and intelligently scales it down to the exact range the motor needs to understand. And there it is, the complete system in action. We're reading an analog value from that potentiometer. Then the map function translates that value in our code. And finally, the code generates a super precise PWM signal to control the motor's position. We've officially closed the loop. We have a physical input controlling a physical output, all managed by just a few lines of code. So let's just quickly recap the powerful little toolkit we've put together here. We started with simple digital output, just making a light turn on. We used binary logic to make those lights actually carry information. We added digital and analog inputs to listen to the world around us. And finally, we used PWM output to create this nuanced analog-like motion. These right here are the fundamental building blocks for almost any interactive project you can dream up. So, we've gone all the way from a single blinking light to a complete working mechatronic system. You now have the core concepts you need to bridge that gap between the digital and the physical worlds. So the only question left is, what are you going to make them do?